Okay, so this is kind of an interesting problem. Let's say that the military has this brand new long distance, high muzzle velocity projectile launcher, howitzer or something like that, that has a muzzle velocity of 1,000 meters per second. And the idea is we want to target some distance, a distance d away, so that we fire at one angle. It takes 60 seconds to adjust this to any other angle. And then we fire a second projectile, and the goal is for both of these to hit the target at the same time. So simultaneous artillery barrage here. And our goal here is to figure out what is the maximum range, maximum distance that we can fire this howitzer so that we can get this simultaneous explosion. All right, so let's say that our launch angle at the higher angle, that's the one that's going to take longer, is theta, and the launch angle at the lower angle is phi. We don't know what those are. They're not given as part of the problem. We're just trying to find d. And we know that the launch speed is the same in both cases. It's the same gun that's firing it in both cases, but you can only fire every minute. So this tau is representing the amount of time between shots at a minimum. Okay, well, let's start by recognizing that since they're both going the same distance, I can use my range formula, right? Our usual range formula here, which is going to be V naught squared over g sine 2 theta for the top one, but has a very similar look for the distance traveled by the lower projectile, the lower trajectory. So notice that in both of these cases, I get a direct relationship between theta and phi. And since they're not equal to each other, it must mean that they're complementary. So from this, we know that sine 2 theta and sine 2 phi are equal to each other. Theta is not equal to phi, or else I wouldn't get two trajectories. So that tells me that 2 theta and 2 phi must differ by pi. One is in the first quadrant, 2 phi, for example, and one is in the second quadrant. So we could write this as, say, 2 theta is 2 phi plus pi. And then dividing through, we can see that phi and pi must in fact be complementary. They add to 90 degrees. Okay, so knowing this, we can now go look at the times of flight, because remember, we have to bake in this 60 seconds somehow. So the easiest way to do this is to say, first of all, maybe I'll label these. I'll call this projectile 1 and projectile 2. The time of flight of projectile 1, we've worked that out before as well. It's 2v sine theta over g. You can just say, take the y component of the velocity initially and see when that equals 0, then double it. And similarly, t2 involves phi. And what we do know about these is that t1, the longer time, has to equal the shorter time plus this firing interval time of 60 seconds. That's how far apart they're firing, because I want to make sure that they land at the same time. Okay, so let's plug those in and simplify a little bit. Okay, I'll go ahead and simplify this by multiplying both sides by g, divided by the 2v naught. Notice that since theta and phi are complementary, I know that the sine of phi is the same thing as the cosine of theta, so I can replace that here. I'll move that over. And now, to solve this for theta, or to use something that we could actually conveniently relate back to our d value here, I'm actually going to square both sides of this. And the reason why is when I square this out, I'll get a sine squared plus a cosine squared. That's going to be 1. And then minus 2 sine theta cosine theta, which is going to give me a double angle. So my final result here is 1 minus sine 2 theta is the square of all this junk. I'll just leave it in its squared form here. Okay, so knowing this, I can go replace my sine 2 theta with this expression involving d, because after all, it's not really asking us about the angle here. It wants to know what is the maximal distance this can go before I can't get this simultaneous landing bit. All right, so there's my sine 2 theta. Solving for d means swapping some things around. And there we have it. This is our maximal distance at which we could possibly fire these two projectiles spaced 60 seconds apart at this given launch speed. And if you're curious, using this 1,000 meters per second and this 60-second interval, what did I get? I got 93.2 kilometers. A possible follow-up to this, you might think, maybe I can ask about when would 3 projectiles hit at the same point. Could you get that to happen? Unfortunately, no in that case. If I have a fixed launch speed, I am only going to get 2 solutions that give me the same projectile range because of this sine 2 theta bit. So unfortunately, we wouldn't be able to get 3 to hit at the same time at the same location. But a slight generalization might be, instead of saying that it's 60 seconds between launches, maybe I could ask, if I gave you a particular omega, meaning an angular velocity at which this thing can turn. Let's say I can fire shells as often as I want, but I want to know omega, or I'm given an omega, the rate at which we can bring this thing up or down as a function of angle. Maybe then, knowing that these two have to be complementary to each other, we could figure out what this time would be, which would also include the difference of those 2 thetas. I bet that would be a much more complicated problem, because now you're probably going to have something over here that is a function of angle, not a trig function of angle. And I doubt that you'll be able to cleanly algebraically get that answer, but maybe numerically that'd be an interesting follow-up. So, interesting question.